home, be in a spot you can take notes and do stuff. All right, I'm recording. Now it started. All right, so going over the quiz today. Hopefully you guys had a chance to go through the book, go through the notes, right? All these terms you should know. You should understand what 95% confidence means. You should go through all this stuff. There was an example on page 481, 482. They walk through this step by step. Since no one asked me questions on it, I'm assuming you guys are rock solid on it. So we'll move on to the practice quiz. You will need a calculator for this, though. Okay, so have that calculator out, or a calculator out that has square roots and stuff, some sort of fun calculator. So some things to note. They ask you a question here, and I like to kind of start by writing out what they told me. So what did they tell me? They say a statistics professor asked her students whether or not they were registered to vote. And a sample of 50 of her students, randomly sampled from her 700 students, 35 said they were registered to vote. So what do we have here? The N that we are looking for, that's going to be our N value. So the number of sampled was 50. Now, this number 35 is super important. Okay, 35 said they were registered to vote. So if we're assuming that she's looking for people that are registered to vote, that's what the topic is. Our observed value, right, our observed proportion, right, the p hat is 35 out of 50, which is 0.7. Our Q value, so the students that were not registered to vote would be the remaining students, right, the 15 out of 50. So I can always take 1, take away the 0.7 to find my Q. Okay, you always to find your Q, you can always take 1 minus your p hat. Okay, so I get 0.3. So that means about 70% are registered, about 30% are not registered from a random sample of 50 students. Okay, something else we should do here before we get started is this idea of what's called a standard error. It's kind of like standard deviation. It's exactly like standard deviation, but it has a different name when we do this topic. Okay, the topic is confidence intervals. So with confidence intervals, we use standard error, not standard deviation. So instead of SD, we use SE for standard error. So standard error of our observed proportion is equal to the square root of P times Q divided by N, but this time it's observed P, observed Q divided by N. When I calculate that, I should get the square root of 0.7 times 0.3, divide that by the sample size of 50. So it looks like a lot like the same stuff from last chapter. It has to do with what's called a confidence interval, and we call it a standard error. Now this one, if you calculate this, okay, if you were to do this, you should get, I'm going to do 0.7 times 0.3, divide that by 50, take the square root of that last answer, and I get a big number, like 0.6, sorry, 48 something rather. I don't know. Let's just knock that down to 0.065. That should be good enough for this problem to the thousandths place. Okay, so my standard error is going to be 0.065. Whew. So what does that mean? What does that mean? What does that mean? Nothing right now. We haven't even asked a question yet. They just kind of told us that 35 out of 50 students were registered to vote. Okay, so from there, I calculate this stuff because I know I'm going to need those numbers. I'm going to need my sample size. I'm going to need my observed value, my observed, the observed success, the observed failure, right? And the standard deviation or standard error from that, okay? You've probably seen this before when they do surveys or samples for things where they say, oh, we did a survey and this is what this is who people are going to vote for with a margin of error of like plus or minus blah, 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 blah. That's what this is, okay? The margin of error is going to come up here in a second, okay? So margin of error is this right here. The margin of error is equal to some z-score. A lot of times I'll have a little star with it, okay? I don't think this book really has it. Let me double check. I've seen it in some books. I haven't seen it in other books. Let me double check to see if this book does it again. I always kind of forget. Yeah, this book does do it. It's kind of like a little Z-star thing. Okay, they do like a little Z-star here. You see that? Z-star. So, all right. So this is all chapter 18 stuff. I'm sure you guys saw this yesterday or Tuesday at least. So going through this, there's a little formula that says the margin of error is some Z value times the standard error of your observed proportion. Okay. Now, the Z star we're going to use, since it says 95% confidence, and we're only going to do 95% confidence. If you guys were taking a stats class in college, they might do a 98, a 99, or a 90% confidence interval, or even something different. Generally speaking, 95% is very common. So with a 95% confidence interval, we're going to use a Z star, okay, a little Z star value of 1.96. Why are we going to use 1.96? Well, let me show you. If I go to 1.96 on my left-hand shaded Z-score table, look what comes up. So 1.9, 1, 2, 3, 4, 5, 6. Okay, hold on. So there's that right there. Okay, 1.96 is 0.975. I'm going to make note of that and show you why it works. So at positive 1.96, it's 0.975. If I go to negative 1.96, 9, 0, 1, 2, 3, 4, 5, 6. At negative 1.96, I get 0.025. Okay, and so what happens when you have this and you go out 1, 2, 3 standard deviations, right? But instead, if we just went out like 1.96 and negative 1.96, okay, and we shaded this whole thing in, but we're going to leave this empty, right? This is kind of like we don't care about this stuff and we don't care about this stuff. So when we say 1.96 left-hand shaded, that was like everything up to that. But we have to take away all this little stuff over here. So we're going to basically take out this stuff and cut off this. So if I find the difference, if I take this and subtract that, you should get 95, right? If I take 0.975, take away 0.025, what's left over is that. So this right here is actually 95% of your numbers. So remember the 68, 95, 99.7 rule? Well, that's an estimation, okay? The actual the better 95% middle interval is actually 1.96. But that's not as pretty. So that's why we're going to use 1.96 instead of 2 for 95% of the middle data of our normal distribution. So usually we use 2 in a very general basic sense, but now that we're getting more advanced, we're actually going to use 1.96 because that's a better set of Z-scores to look at. So we'll use 1.96 as a Z-score instead, okay? All right. So when I plug this in, I'm going to say the margin of error is equal to 1.96 times 0.065. That's the number from right there. Okay, when I do this, I get a 0.1, 2, and 7. So let's pause for a moment. Okay, let me see if I can't get a volunteer. Kelly Klein, you're always an awesome volunteer. Can I chat with you for a minute on this?
Sure.
I feel like I've put zero context to this so far, and I've just been talking about rattling numbers for the last 10 minutes. Would you agree with that statement?
A little bit.
So this question is about a professor in college, I'm assuming, asking her students, because they register to vote, you got to be 18. Would you agree that when she did 50 students and found 70% of them are registered to vote, that 70% probably isn't a perfect number about all kids or all college students? Would you agree that it wouldn't be 70% of all college students? It's probably a little bit more, a little bit less, but it's maybe around 70%?
Yeah.
Cool. So what we're trying to do is we're trying to find like a window. We're trying to set up this big window where if we observe 70% here, if we kind of go out a little bit and out a little bit, we should actually capture somewhere in here the actual true percentage. It's probably in there. Okay. So what they say to do is do this whole margin of error thing. So first you find the standard error, which is like a standard deviation. And instead of going out once, so this would be like kind of like if I take the 70% plus 1 standard error, that's like saying 76%, maybe like 63%, whatever, somewhere in that range. But if you go out to 1.96 of a z-score plus and minus, we're actually going to be doing this 70% plus or minus this number now. And that's going to give us a nice big range from like about 57% to about 83%. So instead of saying 70% just from the class, that might not be the best representation of all students across the campus or whatever. But really, if we go ahead and we're going to add this, let's say plus 12% and minus 12%, we now will have 82%, well, 82.7% and 57.8%, no, 3%. Because it's going to be 0.7 there. So what we're doing right now, we're just getting a range of numbers. So what we would then say is, after we're going to calculate this in a moment, is that we feel the actual true amount. So we're looking at the observed value. We would say the actual true, the actual p-value it has to be, not has to be, but we're 95% sure that it's in there. We're like pretty dang sure that it's actually in that, in this space here between this number and that number. It might not be 70%, it might be 80%, it might be 60%, maybe somewhere in the middle there. So we're just trying to capture where the true percentage is, okay? All right, thank you, Kelly, for that. So one more time, we're trying to do our confidence interval. We take this number, we're gonna plus and minus it to our observed number. And what we're trying to do is capture that big picture. So the observed value, plus or minus your margin of error. Margin of error was this. So p hat was 0.7. Margin of error is plus minus 0.127. So when I do this, I'm going to write it as a set of parentheses where the low number goes to the left side, the high number goes to the right side. So that is an interval. I'm going to say 0.7, take away 0.127. So that's like 70% minus 12.7%. So the small number is 57.3. So 0.5, whoa. And number 7 was stuck in my head still. 573. And then the big number, so if I take that 70%, 0.7, and I add that margin of error, 0.127, I get 0.827. Okay? So when they say 95% confidence interval, that says that we're 95% confident that the true percentage of registered students to vote out of her 700 is going to be between this number and that number. It might not be 70%. We know it's probably not exactly 70% when she goes from 50 to 700 students. It's probably going to change a little bit. Maybe go up, maybe go down a little bit. But we're pretty confident. We're almost 100% confident that it's between here and here. We say 95% confidence because it covers 95% of the this normal distribution that we set up. Okay, so there's a few ways you can explain it. I'm going to explain it a few different ways. There's the easy way to explain it, and that's just basically this. It says we're 95% confident that between this number and this number, the professor students are registered to vote. So so this is more of the slang. If you were doing the AP test, you probably should not write this out. And I'll discuss what the actual better way to say it is in a moment. Now, I might have said the words that it's about all college students or whatever, but we're going to keep it just to the professor's students. Since she sampled 50 of her 700 students, we're just going to keep the bigger group, the bigger population, as just all of her students. Okay, we're not gonna make any other claims because her sample is only from her students. If her sample was from all students around the college, then maybe we would have said the students at the college or something. But she was limited in scope. She only sampled her students, so we're going to assume it's just her students. So that is the basic way to do it. And as I had written this on there on the practice quiz, okay, is that if you wanted to do more of the AP level, okay, the higher level stuff for this is if many random samples of the professor's students are taken, 95% of the confidence intervals would contain the actual amount of students who are registered to vote. That's kind of a more AP way to say it. I like that way as well, but I think this way is just kind of easy enough for what we're doing, okay? If you understand that you're giving yourself room for error. You're basically saying that I'm almost 100% sure that between this number and this number is the actual number of students out of all of our classes registered to vote. That you're allowing yourself a little bit of wiggle room to be wrong. Maybe it's 83%, maybe it's 56% or something, okay? Okay. So, one more time. We got our sample size of 50. We found our observed proportion is 35 out of 50 from the number they gave us, which gave us a p hat value of 0.7. Our q hat value is simply 1, take away that 0.7, which is 0.3. The standard error is similar to the standard deviation. It's the observed p times observed q divided by your sample size, 50, square root that thing. Okay, calculating this out, we get 0.065, and we round to the thousandth place. We're going to use 1.96 because it says 95% confidence interval. I will only have this as a confidence interval for you. If we had more time and it was more advanced class, we would explore 99% and 100% confidence intervals as well. But we're not going to go there today. We're just going to keep that. So I know it's plus or minus 1.96. So I calculate the positive 1.96, and then I add that and take it away from my p hat. Okay, and that gives me an interval, like this wiggle room of, I'm pretty sure the actual true percentage is between those numbers. Okay, once again, we're not sure if it's 0.7 or 70%, but we're almost 100% sure it's actually between these numbers here. Okay. Now, one thing to note, this seems kind of like a big range. Let me chat with somebody for a moment. Let me go to Elizabeth. What's going on, Elizabeth?
Hello.
Hey, so if I was to tell you 57% to 82%, that seems like a pretty big margin, right?
Yeah.
Like, it's useful, but it's not like super useful, right? So how do you think you can make this number even smaller? What do you think could be the thing you could change to make this interval kind of shrink?
I'm not sure.
Okay. So what happens is if you take this sample size and you get a bigger sample size here, what happens is you're actually dividing by a bigger sample size. So by dividing by a bigger number, think about taking like a piece of pizza or a pizza, and instead of cutting it into like 8 pieces or whatever, you cut it into like 100 pieces. And so what happens when you divide by a bigger number is that this number becomes smaller. When this number is smaller, it makes that number smaller, which when you add and subtract makes that number smaller. Therefore, your interval will have a smaller interval around the sample size, which or around the sample proportion. So one more time. It just makes sense that if you have a larger sample, you're going to probably be more accurate with your first proportion, right? So when you have a sample of like 50, it's like, that's not too bad. But if we had like 100, this number would be a little bit smaller because we're dividing by 100 instead of 50, right? This number would be a little bit smaller because we're using a smaller number here. When you're adding and subtracting, because it's a smaller number, this window is going to close in a little bit, okay? So that's going to kind of bring us to a future question here on this quiz, is this idea of selecting a sample size. Thanks, Elizabeth. Appreciate it. I didn't expect anyone really to have that answer. It's one of those things that's kind of like, you know, it's just one of those things in this class they want you guys to consider, okay, is that when they do stuff like this, it's not just, this class is not algebra. It's not calculus. It's not a math that usually has one answer. Okay, it's a more of a science, it's more of a sociology type thing, that if you want better data, you got to collect a bigger sample. You know, if you want more accurate stuff, you simply need a bigger sample. So we'll get to that in a moment. So what's probability that the true proportion of the professor's students who register to vote in this confidence interval? This right here, there is no probability involved. So basically, that's like a trick question. There's no way to answer that question. So yeah, we're not. What they kind of say is with this interval, any number is just as likely as any other number. That 57.3% is just as likely as like 76.2% or 68.5%. They say any of these numbers are just as likely. All you are is capturing a window. You're just capturing a window. Now, if you get more data, yeah, you can say more stuff with probabilities and likeliness of something happening. But there's just simply no probabilities involved with this, okay? That's it. That'd be the answer for that one. Question 4. According to the September 2004 Gallup poll, about 73% of 18 to 29-year-olds said that they were registered to vote. Does a 73% figure from Gallup seem reasonable for the professor's students? Yeah. Yes. Because 73% is within the professor's range of 57.3% and 82.7%. So they said here they took a poll and said 73% of 18 to 29-year-olds said that they were registered to vote, which seems like those are college-age students. Okay, you don't know if they're undergraduate, graduate, doctoral students, so they might be, you know, from 18 to 29-year-olds is a majority of your college students. So does 73% figure seem reasonable? Yeah, it's right in the middle there. Okay, it fits within that range. If it was outside of this range, then we would say it's not, then the figure from Gallup does not seem reasonable if it was outside of the range. Okay. Question 5. On the answer key, I answer it one way, but there is a different way to answer it. I'm going to answer it both ways, and I'm going to show you both ways now. So the first way I'm going to show from the answer key that I posted already. Okay. And what I had posted looked like this. It says, if the professor only knew the information from the Gallup poll and wanted to estimate the percentage of her students who registered to vote to within plus or minus 4%. Okay, so she had a plus or minus of 12%. Okay, her plus or minus was 12% was her margin of error. This margin of error is only 4%. So if she wanted to shrink this number, how could she do that? Okay, how many students would she need to sample? And this is where she's got to bump up her sample. Okay, so how many students would she have to sample? So now what we have is we have our observed value, which was still 0.7. I'm sorry. So we're going to use we're going to back this up. We're going to use the Gallup polls information of 0.73. We're going to use their Q value, then that would be 1 minus this would be 0.27. We're going to use a margin of error of 0.04, and an N value is what we have to find. Okay. So I'm sorry, yeah. So she wanted to. So this is kind of sorry. As I read this, I probably didn't read it. I probably didn't read it to you guys right. She wanted to know, knowing that the actual average is 73%. She wanted to know that if she was to do a sample with her class, would they fit within this proportion? Would they be around 73%? So that's what, yeah. So, and wanted to estimate the percentage of her students who are registered to vote within plus or minus 4% with 95% confidence, right, from that. Okay, if she was using those numbers, not her numbers. So not her numbers, but the numbers from the actual Gallup poll. So it switches from P hat just to P. This is more of what they say is the true value versus just the observed value. The observed value is what you kind of see once. This true value is what's kind of been taken and said to be the actual true value, okay? All right. So we're going to do this. We're going to say the margin of error is equal to that Z star times the square root of P times Q divided by N. But we don't know our N value. Okay, we know the margin of error is going to be 0.04. Our Z star is going to be 1.96 still because it says 95% confidence interval. Yeah, let me use because of 95%. And then our square root of P times Q divided by N will be 0.73 times 0.27. All divided by some N value. So this is where algebra is going to come in. I'm thinking right now, divide both sides by this number, square both sides, and then do a little trick to get this N by itself, right? So let's start by dividing both sides by 1.96. So 0.004 divided, whoops, 0.04 divided by 1.96. Gives me this number here. I'm just going to call that 0.0204. So dividing both sides by that 1.96 gets rid of that, right? And now I have this square root business. Before I multiply that out, I'm going to just square both sides. And that gets rid of the square root. Okay, so I'm going to take and square it. And so now I have, I'm going to put this up here, 0.0, looks like 3 zeros with a 4. That's going to equal this thing here, but without the square root. So I'm going to go ahead and multiply that 0.73 times the 0.27, and that's going to go right here. So that'll be 0.1971 divided by my sample size. Okay. So what I would do from here is I would multiply both sides by N. That would get rid of this, and then divide both sides by the 0.004. And so this is going to be divided by 0.004. So n will equal that 0.1971 divided by 0.0004. I get 492.75. So I would say she should sample, I'm going to round this up to 493, should sample 493 of her students. If she samples 493 of her students, she should get within this number. She should. If not, then that's just weird. But she should be probably within 4% of that number. Oh. So that's method 1. I'll show you guys method 2 here in a moment. I'll just write it down on a piece of paper to make it easy. So I'll put this up like this, and that's kind of difficult to see. This is, you know, this would go there. So I'm going to do a quick algebra problem and call it a day. I still have to put up your book work stuff to post and your quiz to do. So I'm going to go ahead and do this problem like this, and I'll show you the algebra behind it, okay? That if you don't want to do all this, you can actually use like a little formula, and let's create that formula. So what did I do first? I divided both sides by that little z star, okay? So that's canceled out. So I have my margin of error divided by the z star. That's going to equal the square root of p times q divided by n. I then squared both sides. Squared both sides. My margin of error divided by the z star, and it was all squared. That's going to equal p times q divided by n. Whew. And then what did I do? I went ahead and I multiplied into both sides. And then I divided this to both sides afterwards. So I'm going to kind of show that as dividing both sides by that business there. Margin of error. I'm going to go ahead and just write this as, whenever you square a fraction, that means the top number is squared and the bottom number is squared. It's probably going to help me out here. So that little z star squared, all this fun stuff, both sides. All right. So that'll cancel with that. So what do we have? We have our n value is equal to, we got a complex fraction here. We have p times q divided by the fraction of this over this. So the way to do this is we say p times q. When you have a complex fraction like this denominator is going to flip up to that numerator. And that is squared. All divided by the margin of error squared. So this is like, if you guys are good with algebra, right? This is all algebra right here. I know some of you guys say you really do algebra than stats. So there you go. Let's see here. So if that last problem, if I just plug things in, and I said p times q, which is 0.73, whoa, 0.73 times 0.27 times 1.96 squared equals that. Divide that by the margin of error squared. So 0.04 squared. This says 473.2 blah, blah, blah. So it's a slightly different number, right? It's actually off by like 20 people. That's craziness. Why is it off by 20 people? Because there was no rounding at all. So this numbers right here are actually a lot more accurate than what you can do with this because we rounded. Craziness. Okay. So I'll make sure if it's multiple choice on a quiz that the answer should be obvious and not too crazy. Okay. That just if you get a number that's close to what I get, depending on how you round or I round, you should still have a number that's close. Okay. But whenever you square stuff or square root stuff, it always kind of seems to amplify any small things where you round. Rounding changes a lot when you have these squares and square roots. So these notes, I'll put this little formula on the on your notes as well, on your to-do list. But this right here is pretty much word for word, number for number, what we did on the what I already posted on Tuesday. So I'm going to stop the presentation or stop the recording.